In this lecture, we're going to continue diving deeper into a lot of the topics that we learned about in physical geology. We're just going to learn about them at greater depth and with more level of detail. So if you think that you know everything about the Earth's layers, chances are you might learn something, and I hope you do. We're going to start our conversation about Earth's layers in the middle with the core of the Earth. Now, one thing you learned in physical geology was that the core of the Earth is metallic, and that is totally true. It is very much metallic, but how do you think we know? Because we haven't been there. It turns out there's 3 lines of evidence that make a compelling argument for the Earth having a metallic core. And the first one is a density calculation. So I want you to know before we start this density calculation that I will never ask you to reproduce it, but I do want to explain it to you. So you probably remember from some math class or science class that the formula for density equals mass divided by volume, but we're interested here in the density of the Earth. So this is the density of the Earth equals the mass of the Earth divided by the volume of the Earth. Well, it's not like we can put the Earth on a scale and just measure that, right? So we have to figure out ways to be able to get the mass of the Earth first. So if you've taken a physics class or remember any of this from physical science or even earth science, there's 2 important formulas that we're going to merge here. So one is force equals mass times acceleration, and that means the downward force of anything is equal to the mass of that object times the acceleration, typically due to gravity, on that object. So the second force formula that you've probably seen in your life, is this one. This one is used on celestial bodies, so you probably saw this in earth science, where force of an object is equal to big G here, which is just a gravitational constant called Planck's constant. So it is equal to Planck's constant times the mass of that object times the mass of the Earth divided by the radius of the Earth squared. So one of the things you maybe learned in math is that when you have 2 equations and you have F1 here and F1 here, that you can actually set these equations equal to each other. So that's what I did in this next step. The mass of an object times the acceleration of gravity on an object is equal to the Planck's constant times the mass of that object times the mass of the Earth all over the radius of the Earth squared. So you might notice that on either side of the equation, we have this m1 term. That's the mass of the object. So algebraically, we can get rid of both of those. They will cancel out. And if you recall, what we're searching for here is written right up here, the mass of the Earth. So I'm going to rearrange terms so that I'm solving for the mass of the Earth. So the mass of the Earth is equal to the acceleration due to gravity times the radius of the Earth squared divided by Planck's constant. So this is where things get simplified. So the acceleration due to gravity on Earth is 9.8 meters per second squared. So if you drop something out of the second floor window of your house, it would fall at a rate of 9.8 meters per second squared. So G is Planck's constant, and the units on that are ridiculous, but they do work out, where G is equal to 6.6 times 10 to the negative 11th Newton meters squared per kilogram squared. So again, this is just a constant that has been measured by astronomers, but it's a known number. The radius of the Earth is also a known number, and that's actually a much harder calculation. There's all sorts of proportions and relationships that we're not going to get into here. But here's the radius of the Earth. It's an average, right? Because the Earth isn't perfectly spherical. But on average, the radius of the Earth is 6,371,000 meters. So if we plug these numbers in, where we put in 9.8 here, we put in our 6.6 times 10 to the negative 11th here, and we square that number, and we divide it by this Planck's constant here. Oh, I said that backwards. I'm sorry. A is 9.8. R here, we're going to square it at 6.371 million. And then we divide that by the 6.6 times 10 to the negative 11th. We come up with the mass for the Earth. So the mass of the Earth is 5.96 times 10 to the 24th kilograms, which is about 1 million trillion tons. That's how much Earth weighs. It is a 1,000,000 trillion ton celestial object. So remember, we're trying to calculate the density of the Earth. The density of the Earth is the mass of the Earth divided by the volume of the Earth. So we now have the mass of the Earth as 5.96 times 10 to the 24th kilograms. And here is the formula for the volume of a sphere, 4/3 pi r squared. And we know the radius of the Earth is right here, or not squared, cubed, 4/3 pi r cubed. We plug that formula in. The average density of the Earth is 5.5 grams per cubic centimeter. Okay, so how do we use that? How is that useful to us to determine that the core of the Earth is metal? So, going back to our density calculation, if the Earth on average has a density of 5.5 grams per cubic centimeter, and we know that the Earth is made up of the crust, mostly the mantle, and then the core, and we know what the thicknesses of each of those layers are because we know that the base of the crust is the moho and the base of the mantle is the Gutenberg discontinuity. We can also then get an average estimate for the density of crustal rocks. So the density of crustal rocks is about 2.7 grams per cubic centimeter. So that's nowhere near 5.5. We also have some locations where mantle rocks have been brought up to the surface into the crust, and we have evidence of mantle rocks. And we can measure that. On average, mantle rocks have a density of 4.5 grams per cubic centimeter. Again, nowhere close to this 5.5 grams per cubic centimeter. Therefore, based on the thicknesses of these layers and the density of the Earth overall, in order for the average density of the Earth to be 5.5, the average density of the core has to be 10.7 grams per cubic centimeter, because that's the only way you get your average up to 5.5. So 10.7 grams per cubic centimeter is the density of a metal blend, a metal alloy. So there's more that goes along with this. So the density of the Earth indicates that whatever is in the core has to be very dense and likely a metal, because that's what we have on the Earth. The second line of evidence is the similarity between the density measurement and the composition of iron meteorites. So you may remember back in chapter 2, we talked about the fact that between Mars and Jupiter there used to be a planet, and that planet was torn apart by the dueling gravities of the Sun and Jupiter, and that created the asteroid belt. Well, there are two types of meteorites that are found in the asteroid belt, iron meteorites and stony meteorites. And it's believed that prior to being torn apart, that early planet cooled enough that there was a distinct core and a distinct mantle. The composition of iron meteorites is about 95% iron and nickel. That fits with the density that we see in the core, that we can estimate in the core. So we believe that our core and the core of this failed planet are remarkably similar, about 95% iron and nickel. The third line of evidence is one that we can experience every day, that the Earth has a magnetic field, and that those magnetic rays sort of leave the Earth towards the South Pole and then come back in through through the magnetic North Pole. So in order to have magnetic lines of force, not rays, I apologize. I stumbled there because I was like, no, they're not rays. They're not. They're magnetic lines of force. Okay. So we know that most of the crust is created with silica-rich rock. And it turns out the samples that we have from the mantle still have a good amount of silica in them. But silica-rich rocks don't conduct electricity. Iron does, though. Metal does. Nickel does. So in order for us to have a magnetic field, and we know that the outer core of the Earth is liquid, boiling silica-rich rocks wouldn't create the magnetic field, but boiling and convection of iron and nickel-rich rocks would create a magnetic field. So those are the three lines of evidence that the core of the Earth is indeed a metal. Going a little bit deeper to the layer that comprises about 80% of the Earth by volume is the mantle. Samples of the mantle that have been collected are a mixture of iron, magnesium, and smaller amounts of silicon and oxygen. The primary rock type in the mantle is a rock called peridotite. Peridotite is very similar. It's primarily olivine. So I'll show you a picture in just a moment that should hopefully spark some memories. So in fact, let me go to them first. So here is one sample of peridotite, and here is another. And this one probably reminds you more of olivine because it is green. But iron and magnesium can sometimes be a little bit greenish in color if there's more iron, and more black in color if there's more magnesium. However, both of these rocks are made of mostly iron and magnesium with smaller amounts of silicon and oxygen. It turns out that stony meteorites, which are believed to represent the mantle of the failed planet between Mars and Jupiter, also has a composition that is primarily iron, magnesium, silicon, and oxygen. So our inference about stony meteorites being similar to our own mantle is further confirmed by the fact that all the samples of the Earth's mantle that we have collected are also primarily peridotite in composition. So we'll talk a little bit more about how we get those samples later in this lecture. The third layer of the Earth, as we know, and the one that we live on, is the crust. The crust is designated as all solid Earth above the MOHO discontinuity. And we know that that varies depending on whether you're above continental crust or above oceanic crust. And while in 101 we talked about oceanic crust as though it were really just basalt, oceanic crust is a bit more complicated. Oceanic crust on the surface is basalt, but it's actually composed of layers of igneous rock called ophiolites. So here is a figure from your textbook. And if we were to do a cross section through ocean crust, we would find this, what are called ophiolite suites. They are layers of rocks that are found in a very typical sequence from bottom to top. So let's start at the bottom. If we were to go to the base of ocean crust, so just above the MOHO, we would find rocks called peridotite, like we just talked about. When peridotite is metamorphosed a bit, it turns into serpentine. And as we move up through the ocean crust, the next rock that we typically find are gabbros. Gabbro, you might remember from 101, it is an intrusive, dark-colored igneous rock. Then as we move up further, we move into layers of basalt. So there are dike intrusions here where basalt moves up through and cools and eventually flows out onto the surface of the seafloor and forms what are called pillow basalts. And that's what this diagram is meant to show you, is the pillow basalts. Here's a short video illustrating how pillow basalts form. So here you have basaltic lava extruding onto the seafloor, and the cold water causes it to cool immediately, and it forms these sort of lobe-shaped pillow structures that are referred to as pillow basalts. So this occurs along mid-ocean ridges and wherever you have basaltic lava extruding onto the seafloor. Isn't that exciting? All right, so here's a picture of some of those pillow basalts, and what you see on top of them are seafloor sediment. So seafloor sediment can include chert if you're in seafloor that in a part of the ocean that has a lot of dissolved silica in there because chert is SiO2. It is a microcrystalline form of quartz, right? Turbidites are the result of submarine landslides where you have sediment that rushes down off the continents and gets deposited on the seafloor. And finally, in oceanography, if you ever get to take a class in oceanography, we learn about deep sea oozes. And deep sea oozes are basically like sediment that once it is lithified into rock will turn into like chalk. Carbonate ooze is pretty common along the seafloor, as is silicious ooze, plus the word ooze is pretty great. Okay, so this is ocean crust. So how do we know that these ophiolite suites occur? So we find these ophiolite suites sometimes in ocean to continent convergence zones. So we have a collisional boundary here, where here, in fact, this illustrates the collision of the subcontinent of India into Tibet. And we have the subduction of the ocean crust prior to the collision of India with Tibet. So what happens sometimes is that during subduction, there is a process by which part of the ocean crust can get scraped onto the overlying plate. And it gets scraped into what's called an accretionary wedge. So an accretionary wedge is comprised of chunks of ocean crust and seafloor sediment, and sometimes pieces of the continent also that get sort of folded. And the word, when we add sediment and rock to the crust here, the term, I'm going to write it out, it's going to be beautiful, is abducted. So when the sediment is scraped from the subducting ocean plate and added to the overlying continental plate, that isn't called subduction, it's called abduction. And in 1 hour, I will be done typing this out. So abduction is the scraping of sediment and rock from a subducting oceanic plate. Good stuff. And so this is where we will find these chunks of the mantle. So this is how we learn about what's going on, not only in ocean crust, but sometimes little chunks of the mantle will get abducted here as well. And we can use those right along in these ophiolite suites along subduction zones to infer the composition of rock type in the mantle. Oh, I forgot. Sorry. So this gets deposited on the overlying plate or overriding plate. Isn't that perfect? That looks great. Good stuff. So that's what's going on in oceanic crust. Next, we're going to talk about continental crust, which has a density of only 2.5 grams per cubic centimeter. Because it is lower density, continental crust floats on the denser mantle. And this is a diagram that is similar to what we talked about last lecture with the MOHO discontinuity. So here we have continental crust, which is thicker underneath mountains than it is along coastlines. So this series of blocks basically is supposed to take the continental crust and turn it into blocks so you can see kind of how the mass is distributed. So and the idea that the crust, as it gets thicker, that it sinks deeper into the mantle, that is based on an idea that we talked about earlier called isostasy. So isostasy is the idea that the plates float at an elevation in the crust that depends on their thickness and density. So what will happen, from 101, we learned that higher elevations tend to erode faster. And as they erode faster, they shed sediment. So if we think about the fact that the thicker the crust, the deeper it will be in the mantle, as some of that crust is eroded away, which we're going to see in this next diagram. Wait, what just happened? Is that we will have cycles that will create a tremendous amount of sediment. So as these higher elevations shed sediment on either side of the mountain range, it will cause that chunk of crust, sort of the center of this mountain, to float upwards because it no longer weighs as much, right? If we erode part of this block away, that block is then going to weigh less and it will rise up in the crust. So the moho will become shallower at this location, but it will also then create a new highest elevation, right? Now this is still the highest elevation of the mountain. So this will get eroded as well. It will create a cycle of uplift, followed by erosion, followed by more uplift, followed by erosion. And so you can end up with tremendously thick packets of sediment that get eroded from mountain ranges. So here we have our moho, and you can see again that it is deeper beneath continental crust and shallower beneath oceanic crust, and erosion of these higher elevations results in the deposition of sediment here. This is actually what we talked about earlier in chapter 5, that these thick bands of sediment can sometimes subside under their own weight. So as this sediment is subsiding, this chunk of crust is going to bob upwards because it doesn't weigh as much, and it will then subsequently result in more sediment being deposited here in this basin. So it's impossible to talk with any depth about the crust of the Earth without talking about plate tectonics. If this looks familiar, this is actually an assignment that you did as a review in, I believe, chapter 1 or chapter 2, where you looked over the 3 types of plate boundaries, how the plates interact at those types of plate boundaries, what events are associated, what features are associated, and what are some modern examples. So again, this should look a little familiar. You completed this as an assignment. We're going to talk about some of the features at different types of plate boundaries in a bit more detail. So we're going to continue talking about continental crust and what sort of features that we see at convergent boundaries on continental crust. And here's another new term for you. So the term I'm going to use is called allochthonous terrain. Oh my God, it's such a great word. Say it, allochthonous terrain. Yes. All right, so that it is a region of metamorphism. Typically you have allochthonous means foreign, and so they're whole terrains that originated somewhere else and have been accreted onto a continental margin. You can have chains of volcanic islands that are accreted onto a continental margin. You can have microcontinents that are accreted onto continental margins. Here is a series of allochthonous terrains that are found along the west coast of North America, and you can see they're all labeled. So really what we're going to learn is that really from the Mesozoic on, all of the terrain that you see here colored in has been added to North America from the accretion of chains of typically volcanic islands that, as we've had subduction of the oceanic plate here, a lot of times it will be carrying island chains with it, and then they just kind of get accreted or glued on to the west coast of North America. Sometimes, and you can see the extent of these allochthonous terrains, sometimes when we look at the east coast, we can see an even larger example of an allochthonous terrain, and that is a microcontinent that is known as Avalonia. So if you kind of imagine a dividing line along the Appalachian Mountains, everything to the east of the Appalachian Mountains is part of a microcontinent that has been accreted onto North America called Avalonia during the Paleozoic era, and proto-North America has been called Laurentia. And so you can see here the dotted line where Avalonia was added to Laurentia as an allochthonous terrain. An example of a modern allochthonous terrain might be Madagascar. That's large enough to be an allochthonous terrain. You could argue that India, as a microcontinent, is too big to be an allochthonous terrain, but nevertheless, that is an addition to Asia as well. Okay, so the third term that students often confuse with allochthonous terrain and accretionary wedge is called melange. And I've been accused of pronouncing this in a creepy way. That is just, it's a French word. A melange is a mappable unit of rocks that have been folded and in some cases transported. And so the melange in a convergent boundary is the part that gets squished here. So when we have a subduction zone, we know that on the overriding continental plate, we have a chain of volcanic islands, also called, or not a chain of volcanic islands, a chain of volcanoes like the Cascade Mountains, where we have the subduction of an oceanic plate beneath North America. So you have like Mount St. Helens and Mount Rainier, Mount Adams are part of the Cascade Mountains. And then we know now that there are chunks of the subducting oceanic plate that sometimes gets accreted onto the overriding plate, but the accretionary wedges that are subducted are actually part of what's called the melange. So the melange is not only anything that gets abducted, but it's also rocks that get metamorphosed right along in this convergent boundary because you have really high pressures but low temperatures because you're at a shallow depth in the crust. So lots of rocks in the Pacific Northwest, especially between the the Cascade Range and the Pacific Ocean will have this sort of texture where you can see the rocks have been heavily metamorphosed and they're no longer in any sort of like original orientation. And they're large enough that these melanges can be mapped. And again, they're typically between the oceanic trench that's created along the subduction zone and the volcanic chain as well. So you're going to have an assignment playing with those three terms: allochthonous terrain, accretionary wedge, and melange, because they're all kind of associated with convergent boundaries, but they differ in scale, and they differ, I guess, in how they form. So a lot of times accretionary wedges can get abducted and become part of these melanges. But the accretionary wedges, remember, are abducted chunks of the ocean crust. So that will be ophiolite suites as well as any surface sediment along the seafloor. Good stuff. So that's what we're going to learn about with convergent boundaries. Divergent boundaries that we're going to talk about are pretty straightforward. So divergent plate boundaries, as we know from 101, are locations where plates move apart from one another. And most commonly this occurs at mid-ocean ridges. The mid-ocean ridge system is about 42,000 miles long. And we know that sometimes we can have rift zones, continental rift zones, that exist when you have divergence beneath the continents. And this is a picture of the Afar Rift Valley in Africa along the East African Rift Zone in Ethiopia, where you can see lower areas here, and you can see that there are drop-down blocks here, and this is where the crust becomes thinnest. You can see that there have been basaltic lava flows here. You can tell that from sort of the texture and the color of the rocks here. Basaltic lava flows are common at mid-ocean ridges, but they can really form anywhere where the crust is getting thin, and you start to induce melting in the lower crust. So that's exciting. So rift valleys can eventually widen to become mid-ocean ridges, right? And we know that that's the likely fate of the East African Rift Zone, is that in 10 million years, the East African Rift Valley will pull apart from mainland Africa and be its own sort of microcontinent. What there's plenty of evidence for in the east coast of the United States is a phenomenon called a Wilson cycle. So the Wilson cycle is named after a Canadian geologist named Wilson, who came up with the idea that the opening and closing of an ocean basin may actually be cyclical, which is really cool. So you have the initial opening of an ocean basin along a MOR, or a mid-ocean ridge system. So you have these rifting events that can occur in continents to the point where you begin to create a mid-oceanic ridge. So here you have a continent. This is a very simplistic model, but it does the trick. So you have a thick continental chunk of crust, and you have rifting. So this will create rift valleys. This will also create basaltic lava flows, as you have what's called decompression melting that occurs in the rocks in the crust. And then eventually this will occur until you have two separate pieces of continental crust characterized as granitic rock, and then you have a much thinner oceanic plate characterized by basaltic lava for the most part, that separates these two new chunks of continental crust. And this will continue until convection in the mantle changes. So the idea of a Wilson cycle is that ocean basins will open and then ocean basins will close. And that this has happened on almost a cyclical way in a couple places in the earth, where you can see down here the spreading of a divergent plate boundary reverses as convection currents in the mantle reverse. No one really knows why these occur. We just know that there's evidence for them. It's very cool. And this cycle from opening and closing of ocean basins is approximately a 500 million year cycle. So to illustrate that, we have this very simple model here in this 30-second video. That is not high tech, but basically it illustrates the same principle, is that you have continental crust that spreads, and you begin to have the generation of rift valleys, and you have volcanic eruptions through faults in the rift valleys. This will continue until you have the formation of oceanic crust separating these two continents. You can see that they're still upwelling from the mantle and then spreading out, which is very characteristic of divergent plate boundaries. And this will continue until you can see that those mantle convection currents have changed. And now instead of diverging, we have converging here. And we have the closing of that ocean basin and the creation of that same, well, in this case, it's the same two chunks of crust. It's not always the same, as we'll see in the next slide. So this is, the Wilson cycle is also connected to supercontinental cycles, so that you have supercontinents like Pangaea, for example, and they break apart. And you have the opening of an ocean basin, and eventually that ocean basin closes, and the continents come back together and create the next supercontinent. So let's see what that looks like in North America. So this slide goes from bottom to top. Or in the mid-Proterozoic, about a little more than about 1 billion years ago, there was a supercontinent on Earth, and it was called Rodinia, and it was created by a large orogenic event, a large mountain building event called the Grenville orogeny. It created the Adirondacks as we know them today, in part. And you can see that this is a convergent boundary. And Rodinia was a supercontinent. It was the supercontinent that existed prior to Pangaea. And then what we see in the late Proterozoic is that no longer is there convergence, but there's divergence. And it opens what will eventually become the Atlantic Ocean, but it's actually called the Iapetus Ocean. Iapetus, I think, was the father of Atlas in Greek mythology, and so the Iapetus Sea, and the Iapetus Ocean, is the predecessor for the modern-day Atlantic Ocean. So we have widening, we have spreading here, and then you can see that there's more closing of this basin that follows that. So you have convergence, divergence, and then more convergence. And we see this, the evidence for this convergence in North America, because there was an island chain called the Tectonic Islands that were added to North America during the Ordovician period. And then Avalonia, which is the microcontinent that we talked about, also was added to North America as we had continued convergence in the Devonian period. And what you see coming here on the other side of the Iapetus Ocean is Africa. So Africa slowly comes and collides with North America in the Mississippian period and the Pennsylvanian period, creating the supercontinent of Pangaea. So to recap, we started with the supercontinent Rodinia. It broke apart and created the Iapetus Ocean. And then slowly we had closing of the Iapetus Ocean and the creation of the next supercontinent, Pangaea. Now, Pangaea broke apart around 200 million years ago, and the Atlantic Ocean has been spreading ever since. So that is an example of a Wilson cycle, the opening and closing of an ocean basin. So we covered a lot of territory in Chapter 7. We learned about seismic waves and how we use them to study Earth's interior. We learned how we use seismic waves to identify discontinuities, changes in the layers of the Earth. As we go deeper into the Earth, we identified 2 discontinuities, the Moho discontinuity at the base of the crust and the Gutenberg discontinuity at the base of the mantle. We talked about the layers of the Earth, how the core of the Earth is metallic, and we know that for 3 reasons. We know that it's metallic because of the density of the Earth. We know that it's metallic because it is similar in composition to iron meteorites, and we know it's metallic because the Earth has a magnetic field. We know that the Earth's mantle is predominantly peridotite rich, meaning that it's iron magnesium rich with a little bit of silicon and oxygen. That's similar. We can actually collect some samples of the mantle at accretionary wedges, and we can also infer based on the density that it is likely peridotite rich as well, and it is similar in composition to stony meteorites. The crust of the Earth, which we already knew, was divided into oceanic and continental crust. We learned about it in a little bit more detail. We learned that oceanic crust isn't just necessarily a layer of basalt, but it's actually several layers of very dark, dense rocks called from peridotite to gabbro to basalt to siliceous and carbonate oozes on the top of those ophiolite suites. And we learned that the continental crust sinks deeper or more shallowly in the crust depending on the presence of mountains. Then when we were talking about the crust, we diverted to talk about what sort of plate boundaries and features that we see at plate boundaries. So at convergent plate boundaries, we saw that chunks of oceanic crust can get abducted onto the continents into what are called accretionary wedges. Accretionary wedges can be part of a melange, which is the area of the continent that not only includes the accretionary wedge, but any rocks that get folded and metamorphosed along the boundary between the ocean and between volcanic volcanoes. Finally, we can have entire microcontinents or chains of volcanic islands that get accreted onto the perimeters or the sides of continents, and those are called allochthonous terrains. Finally, we talked about how divergent boundaries are characterized by opening and spreading along mid-ocean ridges, but they may actually be part of large-scale Wilson cycles. All right, that was a lot. Hopefully this makes sense. Ask questions if you have them, and you will have a quiz on all of Chapter 7 following this assignment.